Good evening, everyone. Welcome to Mathematics Colloquium. It is my great pleasure to introduce Professor Isidro Munive from the University of Guadalajara, and he works on the regularity theory of partial differential equations. And today he will talk about the boundary Schauder estimates in Carnot groups.
Well, thank you for the introduction, and also thank you for the invitation. It's the second time I come to this institute, and in my first visit, actually, we start thinking about these Schauder estimates in Carnot groups. I will mention some of the results we got back in that time, and so just to remind you, what are the Schauder estimates in the Euclidean case, and so well for the Laplacian, no? So as you can see, these are if you have a function f and in ck minus 2 alpha and g in ck alpha, then we have this estimate, no, on the solution u. Okay, so what about the proof? How do you prove this type of estimates? Usually, well, if you see the book by Silva and Savin, you will see the proof is basically potential theory. No, they use the integral representation. By that I mean fundamental solutions, and then there is another technique I will mention. But the idea now of this talk is to give another approach, no? Something that is, some people think is more flexible. This fundamental solution might be too rigid for some people. And so the idea is to, well, to get some ideas from Caffarelliin and from Silva and Savin, okay? So why do we need those type of ideas in this setting of Carnot groups? I will describe what are Carnot groups, no? So you have some idea what we are talking about. So in Carnot groups, this reflection technique cannot work, no? You have a solution and a flat boundary, you reflect, and then you have another solution. No, you cannot do that in this subelliptic setting, no? So a little bit of history of Schauder estimates in the Carnot group. The first one is due to David Jerison in 81 in the Heisenberg group. I will mention what is the Heisenberg group in a few minutes. And so the Heisenberg group was a rich structure. No, it's a Carnot group, but it's also a CR manifold. So it's probably the most important Carnot group that you can think of, no? And so he uses a lot of like harmonic analysis to prove this type of Schauder theory. Estimates, and the point here is that he does it in non-characteristic points. I will talk about what is a characteristic point later on. And also, well, this paper, this was the one I was mentioning with Agnid and Garofalo. We start thinking about this type of problems in my first visit. So we have a Schauder estimates near C1 alpha, Euclidean C1 alpha, in a portion where there is no characteristic points, no, and the idea was to use some arguments by Caffarelliin. No, now we try to implement this in this setting for k bigger than 2, these ideas, but we really needed some other approach, no? So we have to combine Caffarelliin's ideas with the Silva and Savin. Okay, and also there is some other method by Banerjee and Cupini, where they use some potential theory to prove Schauder estimates, but they prove it for k equal to 2 and also in smooth domains, no? Okay. If you can see, we do it in C1 alpha, no? So that's a very big difference. And also they have some geometric assumption on the boundary, no? So they have to assume that they use distribution at the boundary, verify some Hofmann condition. You know? Okay, so very restrictive. No? So there is another paper that I didn't put here of GT, Yannick and some other person where it seems like they remove this restriction, but they only do it in the Heisenberg group, no? In the first Heisenberg group, no? Instead of HM, they just do it in H1, okay? So it's I think it's last year they put it on archive, no? So what is a Carnot group? So well, it's a Lie group and it's a tangent space identity can be stratified, no? And this is the stratification, no? So G can be written as G1 sum of the G sub R, and G1 generates the whole space, no? So that's the second condition, no? Okay. So these groups were introduced by Gerald Folland. Probably, I hope I don't make a mistake, but it seems like he introduced this in his 1975 paper, the subelliptic estimates and function spaces of nilpotent Lie groups. Okay, so he was just thinking about, you know, the theory of Hormander and Conan-Nirenberg. So he wanted to do some subelliptic estimates, but in groups where more, well, in settings where you have more structure, no, like these groups, no. Okay. So then Stein, he started thinking about the Stein and so on. No? A lot of activity has been going on in this setting of Carnot groups. Okay, so let's discuss more properties of these Carnot groups. So since the group is simply connected, we have a exponential map, is a diffeomorphism. So we will use this exponential map to build some coordinates, okay? And so that will make things more simple to understand. Some people, when they introduce Carnot groups, they immediately say it's just simply like Rn, and they give the group law, no? So in this case, we opted for doing this in the more general way, because you can choose other type of coordinates, not just the exponential coordinates, and the group law will change, okay? So usually we identify, we will denote by E the identity element, and we, for a point P, we associated with these exponential coordinates, no? So P is equal to exponential C in with his logarithmic pre-image, okay? So the first layer has an important name, no? So it's the horizontal layer, so it's the one that generates the whole Lie algebra. And also, we can put some scalar product on the Lie algebra, so to make it a and also to make it these vector spaces GJs mutually orthonormal. Okay. Moreover, we define these dimensions Mj, and bigger N is equal to the sum of all these dimensions. Okay, so that's the topological dimension. No, so we will see that. Well, you can also see that the Schauder dimension is different than this type of dimension. No? So since the first layer is very important, we just call M equal to M1, no? So to distinguish that one, okay? So that's the dimension of the first layer. So how do you get the group law using this exponential map? Well, you use the Baker-Campbell-Hausdorff formula, no? So if you put the relations of the bracket relations at the level of Lie algebra, you get the group law, no? So, okay, and so since we have an orthonormal, so we have as a dot product, we consider an orthonormal basis of the horizontal layer, and we associate with them left invariant, a family of left invariant vector fields, no? So these are given by xj, which is here LP is the left translation, okay? Okay, so just to recall what is a left invariant vector field, well, it's just LP related, no? Just that's the definition. And also you can see that the action of xj on a function is defined by 2, no? So if you want to be more explicit, no? We can also define other vertical vector fields, no? Using the same ideas, okay? So, but the relevant ones are these xj's. Moreover, so we can give a Riemannian metric in G, and also, so we consider this horizontal gradient like the projection, no, of this of the gradient into this horizontal layer, no. And moreover, so the relevant operator here, the one that plays the role of the Laplacian, will be this operator called the sub-Laplacian, okay? And so here x1 through xm are these vector fields, okay? So these are this is the relevant operator, okay? So you can see that this operator comes as the minimizer of this energy, no? This given by the gradient, no? You can think of that, no? Also, well, we have a distance in these Carnot groups. And how do we define the distance? Well, using this exponential map, no? We can define, we have a Euclidean distance in the first layer, and we push it to a distance in the Carnot group, no? So the idea is using these exponential coordinates. So we have P, then we define its distance or its norm by means of the exponential map, no? Okay. So recall that P can be written as this exponential map, no? Okay, so C1 and CR, all of them are in the respective layer, okay? So the name of this function is the non-isotropic group gauge, okay? So this is not actually a distance, okay? So, you know, the triangle inequality is not satisfied. You know, if the constant instead of being 1 is some other constant c, okay, but you still have some good distance, no? You have also another type of distance, which is the Carnot-Todori distance. That one is more involved, and probably for doing analysis is not very good because you cannot do computations, no? So if you want to do some computations, maybe this one is much better, no? Okay. And also, well, what are these? These Carnot groups have a very rich structure. So we have some dilations, no? And so the dilations depend on the layer. See, yes.
Like, why did you call this
non-isotropic? Well, I don't remember now.
No, every layer is still different.
So well,
but it's the same formula, but each level is different.
No, it's like a line can become like a quadratic in the high layer.
So you need this. So you need this because you have these rescalings, no? So depending on the layer, you have these rescalings. So so it depends, like the parabolic. When you have these rescalings of the parabolic in the heat equation, you have x rescales linearly and the time rescales quadratically, no? So you can think of this, if you want to have a picture in mind, it's like that, no? So different rescalings, no? And so, well, I mean, P can be written like that, no? Okay. And so, well, this distance is like homogeneous of degree 1, no? Okay. And so the distance is also homogeneous of degree 1, okay? And also we have this, what is a homogeneous, a function of homogeneous degree? Well, this one also, delta lambda of is just lambda to the power k of f, okay? And also we have what is a homogeneous vector field, which is given by this, okay? And one can check that these xj's are homogeneous degree, vector fields of homogeneous degree 1, okay? So we come to our most important example. So I just give this already in these exponential coordinates. So the Heisenberg group is the underlying manifold is R to the 2n plus 1, and the group law is given by this. Okay. So I guess people that work in several complex variables already know this type of groups. No, it's a CR manifold. No, it appears as the boundary of a pseudo-convex domain. No, so well, we are not looking at these properties, so we are just looking at the group properties, and then so a basis of the Lie algebra is given by these vector fields. Okay. And so, well, so we can see that this the Lie algebra of the Heisenberg group is given by this stratification, and because of this, this relationship. And so we can write the sub-Laplacian in this group is given by this, okay. So well, if you see this formula, you probably won't be very surprised, or excited, but it has a lot of connections with another type of operation, which is about some Grushin operator, okay. So this part is like taking the derivative with respect to some rotation we can think of, So when n is equal to 1, so if you have a function that just depends on the norm of C, this part will disappear, and you will get that another operator, So this operator has a lot of connections, and the important thing is that this is not elliptic, okay? Why? Because we are missing a direction. If you miss a direction, so we are missing the t direction, So it cannot be elliptic, okay? So if you write the matrix, and you will see that this is not an invertible matrix, It's non-negative, but you cannot. It's not elliptic, because you are missing one direction. So you have to develop so this is a different type of animal, So the whole geometry degenerates, Some degenerate equations degenerate in some points, particular points. But this one is completely degenerate, The geometry is not Riemannian, Okay. And well, you have here the Laplacian, in these R2n variables, That will be important later on. And so, well, I've mentioned some works of David Jerison, and this is a very important contribution in this subelliptic setting. So he was working in the 80s, and he came up with this example. So he considered this paraboloid, okay? And so he showed that given any exponential alpha, you can cook negative constant m, for which there is a positive solution in this domain, okay? That cannot be better than this, Okay, so you cannot expect more regularity, all the regularity, near this point, okay? And the problem is that, well, there is a geometric phenomenon going on. So this means in the origin, this is what happened. This is the normal. So this is orthonormal to the first layer, So you lost a lot of information, in those type of points. There are some works in regularity in these points. You can see some papers of Garofalo, Caponia, you mean. So not every characteristic point is that bad, So you can do some estimates near characteristic points, okay? But this turns out to be really bad, So the idea is to stay away from these points, For that, well, in order to state our main result, we need some more definitions, These are Holder spaces introduced by Folland and Stein. Okay, so here this is the gauge norm, So this really looks like the Holder norm, but we change instead of Euclidean, we have this norm. We define this semi-norm, and moreover, we for this multi-index, we define this iteration of derivatives. Okay. And so finally, we have our spaces, These are the Holder spaces or the Folland-Stein spaces where this quantity is finite, no? So let's make it more precise. What is the meaning of characteristic points, no? So you have a Euclidean C1 bounded set, so and a defining function, phi, no? Then what is a characteristic point? Well, as in the case of the Heisenberg group, is where this the gradient is, well, you can actually say that the norm of the horizontal gradient is 0, no? Okay, so we want to really stay away from these points. Okay, so if you stay away from these points, things are not that bad, no? So Kohn and Ehrenberg and so on, and Derrick proves this result. If you stay away from characteristic points, you have all the regularity you want. Okay, so if you have if omega is infinity and we have a weak solution of this problem, and we don't have characteristic points, then we have all the derivatives we want. We have this estimate. This estimate will be important for us in our theory of Schauder estimates. Okay. No? It's a weak solution. Just think like in the Sobolev spaces. Sorry. In equation 6 is just maybe I made a mistake. It's just you want to stay away from the characteristic points, no? So it's a local problem. So the important thing is that it's a local result, no? It's not a global result, no? So you want to stay like near this non-characteristic point, no? Okay, so well, this is a typo. So the idea is that if you are away from characteristic points, things are not looking that bad, no? So the interior estimates, they have been established in the, well, first in the 90s, and then Luca Capogna like recently. So if you like, for instance, if we have a solution in a ball of radius 1, we have some interior Schauder estimates. No, so I think Xu, well, he did it for more general operators, not for Mander type operators. No, those for Mander type operators well are too general, and so he did more like potential type of estimate techniques. And Capogna and Han, well, they started doing this type of Caffarelliin type of arguments, no? So it was point-wise. If you look at the paper, it's just point-wise Schauder estimates, okay? So the interior is fine. So we have some interior estimates, okay? So these are just the, and also Gutierrez and Lanconelli have some estimates, interior estimates, but they just do it in C2 alpha. I mean, well, gamma 2 alpha, no? Okay, so I'm implementing some ideas also of Caffarelliin. Well, so in Carnot groups, we actually have like a Taylor formula, no? So for that, we need the notion of homogeneous polynomials. No, in general, for Mander type operators, that we don't have that, and that is like one of the main reasons why this type of the arguments that we will be discussing cannot be applied. No, so there is a big missing piece. No, okay. So there is a very important distinction between Carnot groups and general for Mander type of operators. No. So well. Since we were talking, we were saying that different layers have different weights, no? So if we have some multi-index I, so depending on where you are weighted differently, no? Okay, so usually we just the multi-index we just sum all the indices, no? But in this case we put a weight, no? So you depending if where you are, you put a weight, okay? That's because this is non-isotropic, no? And so these are called the homogeneous length. And So, well, for simplicity, well, you can see a monomial here, no, and so the homogeneous degree will be like this one, no? Okay. What is a homogeneous polynomial? Well, it's a polynomial that can be written in this way. And the homogeneous degree is the largest of these quantities that for which AI is different from zero, no? So as I was saying, we have a stratified Taylor inequality, no? Which will be really important for us later on, no? So it really looks like our Taylor inequality in Rn, no? Where instead we are here taking a polynomial homogeneous degree k, no? Okay, so this is the meaning of that. So the first derivatives just agree, no, in the identity, no? Okay, and we have this road, no, which is going to be very important. All right, so well, this is a lot of background, I guess. So let's start with our main result. Now, what is our main result? So here we have a matrix. Now it's m by m. Usually it's n by m in the Euclidean case, but now we are just considering the dimension of the first layer. And so it's elliptic. No? And also, well, I think the things that you were asking is this like this V, no? In the last theorem, this I forgot to put this one, no? So you're localizing the problem, no? Okay, so you don't touch characteristic points, no? Okay, and so we assume this is a very good assumption that we do is that we are assuming that the boundary is ck alpha, no? Like in the paper of Chitty and his collaborators, they only assume it's smooth, no? So we were able to establish other estimates for this type of domains, no? So we assume we have a point and about this set doesn't have a characteristic points, and we consider a solution of this problem, no? With this hypothesis, okay? These are like the standard hypothesis in Schauder estimates, no? We are changing C for this gamma, no? Okay. So we have this Schauder estimate, no? So it just looks like the Euclidean one. So instead of having this, the usual partial derivatives, we have these vector fields, no? Okay, so we have this regularity on the gradient of U. So how do we prove this main result, no? So we were, at the beginning, we were thinking like pushing the ideas in our C1 alpha paper, but it was getting kind of complicated, no? So, I mean, in the literature, people say, okay, you can get these estimates, no, by applying some ideas of Caffarelliin, no? But in reality, we found out that these are very hard to implement, no? We were having a lot of problems. So we were looking at some papers by Silva and Savin to get more inspiration. So it's a combination of these two type of ideas, no? So we give a lot of credit to this new paper of Silva Savin, no? Okay. And also one can think of compactness methods is plus these ideas of Silva Savin, no? Okay, so for simplicity, we can always remove the boundary data, no? And assume that it's zero, no? So that's what we do. Okay, and also since we have translations and rescalings and rotations in the first layer, we also assume that this happens, no? S or radius is 1. We are at the origin, and also, well, at the identity we have AIJs is just the identity matrix, no? Okay, so that's not a big deal. And also we can express our or domain as this one, no? So H is C1 alpha, no? Okay. So let's start our process, no? What we do first is do some preliminary reductions. Okay, so we take a sigma between 0 and 1, and we are rescaling all these our domains, no? So when we rescale our domains, well, the domain will look like this, no? So as you can see, things rescale differently, no? This one is sigma squared, so they decay at different rates, no? And also the graph is given by this, no? So as you can see, we have now it appears this 1 over sigma that will play a crucial role later on, and also for just to make things simple, we denote by d the distance function. Okay, so this distance function, since the domain is very nice, it has very nice properties, no? Okay. So for instance, we can write the distance like this, no? Okay, so we have a term that appears, no? In the Euclidean case, we just have one, okay? So in the non-Euclidean case, we have this gradient of the distance, okay? And so we have this polynomial of degree 2 and something that decays in this rate. Okay, so what can we do is using this 21, we can always assume that, you know, this function is very small, no? This norm, no? Okay. And also, so since we are removing this part, we can also assume that this growth happens with the distance, no? Okay, so this is the distance function. And so we get a new boundary problem, no, with this sigma. Okay. So the idea is that when sigma is really small, we will get something like, so this, the aij's will become like the identity, no, and this is this h will become like 0, no. So we will have something like xm equal to 0, no. So this function will be very small, no. Okay. So then we have this new boundary problem, no? So the sigma will be later on fixed, okay? And moreover, given some delta, we can assume that this happens also, no? Okay, so this delta will be chosen later, no? So we choose delta and then we choose sigma, okay? Okay, so what are the steps in this for the proof, no? So we prove first that there is a k-order Taylor polynomial at every point, no? So with that information, we prove that the derivatives of the boundaries have this Holder continuity, and with that, we prove that the derivatives of the boundary have this Holder continuity, no? So these are the steps, no? And for that, we need this approximating polynomial, no? Okay. So if we have a solution, no, Lu equal to f, we say that a polynomial p is of degree less than or equal to k minus 1 is k order approximating for this equation if this happens, no? So the Taylor polynomials will, in some sense, match, no, in the identity, no? The Taylor polynomials of LDP and of f, no? This will be very important later on. Okay, so this is an idea that I guess is from the Silva Savin, no? So this is the new thing, no? Done in our C1 alpha paper, no? Okay, so why? Because we changed our compactness lemma, no? So we were thinking of getting a compactness lemma like in our C1 alpha paper, but it was getting a little bit complicated. So we adopted this this notion to set this compactness lemma, no? Okay. So as before, we have a solution, and then so we start by assuming that there is an approximating polynomial that satisfies this, no? Then we can find a better one, no? That's the whole idea. No? Then if delta is small enough, the delta that I told you before, so gives you the smallness. We can find this row for which we have this decay, no? Okay, moreover, well, this polynomial satisfy this this thing, no? So if one looks at this term, you will see that at the boundary it becomes zero, no? So it really captures, no, that we are dealing with zero boundary value, no? So things are getting better because of this. So the idea works because of this distance, no? Otherwise, if we don't have this distance, well, we couldn't capture really how is the boundary values are zero, no? Okay.
We could do it up to 2.
Up to 2 we could do it, but then we realized, oh, okay. And then we say, okay, we were getting a lot of troubles, and so we say, okay, this idea is much efficient, no? Okay. So I think nobody has done these Schauder estimates using these ideas, no? There are some lecture notes by Rosoton that they describe some type of compactness argument, but it's not really.
So just one historical reference. So the thing is that this notion of approximating polynomial without being molested by us, Savin and Silva does it in the context where they prove higher order boundary probability. Higher order boundary Carnot. So they don't do the distance function.
Okay. Yeah, so they have a different setting, no? So
that U is also a solution, so you apply to.
yeah, exactly. So this idea is it's new when we change that for this distance, okay? So we believe these ideas can be implemented in another type of context, no? And probably they are more flexible than this potential theory, no? So how do we prove this type of compactness arguments? So the idea is, well, you have this approximating polynomial, and then you consider this function, no? Okay, and then you apply this operator. Okay, so it's just a rescale version, no? So you notice that since this is like since P is an approximating polynomial, well, this side will have this trait, no? So you can bound it by 1. No? So that's the important thing, not to notice. Okay, we also have this, no? Since f is in gamma k minus 2 alpha, we have also this estimate, no, by the Taylor expansion, no? Okay. So we have this, no? So since this is an approximating polynomial, we have this expression, no? This omega decays in this rate, okay? And so we have that. I was thinking that this side, sorry, this. So this comes from 27, and this one comes from 29. Okay. So this is approximating polynomial. Okay, so you notice that, well, so delta can go to 0, no? In some sense, we can just let it. So we will have and this L will tend to the identity. So it's not very hard to prove that, you know, a compactness type argument, that if for every epsilon that you give me, we can find a small long delta for which we have this solution, and this solution is very close to our solution B. Okay. Yes. So this is like the type compactness argument, no? So we use the properties of B0 to show properties of B. Okay. Usually, well, in the Euclidean case, they just reflect this. They can reflect this if, for instance, we are in Rn, no? you get the estimates on B0 by just reflecting, no? When xm is negative, no? And then you get a lot of properties, no? But in this case, we cannot actually do that, no? The whole structure will be lost, no? So you might get some Hormander vector fields and you lose the group structure, no? You can try this, no? You can just put your hands and then try to see if the reflected solution is, well, the reflected solution is also a solution, but you will find out, oh no, you destroy the whole group thing. But this is not that bad, no? Okay, because this is a non-characteristic plane, no, domain, no. So we have the results of Kohn and Nirenberg. So that says that after some extension, just to preserve some regularity, we have this bound, no? So V is as regular as V1, no? So with that, using this, we construct a polynomial of degree less than or equal to k minus 2, like this, no? So V0 can be approximated like this, okay? And so now, given this alpha, we fix rho that behaves like this. So this will be like our epsilon, no? Okay? So we fix an epsilon, then we have a delta, and then we have a sigma, no? Okay? So you see, we take sigma, and then since B is close to B0 and B0 is close to xm cube, we have this estimate, no? So there are some technicalities, and what we really want is to, at the end, show this estimate, no? So we get something like the thing we want, no? So we want a polynomial, no, like this one. So we are almost there, no? We get this polynomial, no? So since we are imposing that the polynomial should be an approximating polynomial, well, nothing tells us that this will be approximating, no? So we have to modify this Q a little bit to some Q tilde. So, and so we don't change that much this estimate, no? This estimate 38. Okay. So how do we do that? Well, so Q, we just suppose that is given by this, and Q tilde is given by that, no? And so we need to show that this is an approximating polynomial, no? So we already know that P is approximating, so we have half of the battle already won, no? So by doing some computation, this part is already this one, so this should be like 0, no? And then we notice that, well, L is like a perturbation of the Laplace, the sub-Laplacian, no? Okay, that will be really helpful. So this is the thing I was telling, no? So the Taylor polynomial will be 0, no? In some sense. So recall that we have this expansion of the distance. And so what we do is, well, so we are interested like in the Taylor polynomial of this this expression, no? So how do we get this like a Taylor polynomial? Well, first of all, we notice that it's really good that this one is Q is xn times Q is harmonic, no? So we use this idea, no, that we can decompose the operator as that. And so remember that we're saying that Aij minus Aij is very small, no? So we're saying this reduction, no? It's like very small, this delta, no? So very close, no, to each other. So we use this idea, and then we have we break it like this, no? Okay. So why do we do this? Is that we actually want to write this expression as the sum of r plus omega. Omega is has this decay, and r is this polynomial, no, of of degree up to k minus 2. Okay? So we really want that. So then it becomes approximating, no? So this thing will disappear, no? So, well, in order to well show that these coefficients can be found, we have to do a lot of heavy computations and to find a linear system for this p tilde, no? So by using all these sublaplacian, no? And it's quite involving the computations. Okay, so hopefully, so the paper will hopefully come out soon, and you will see how you know, in order to find these coefficients, we have to, it's a system, and we notice that we can solve the system, no? Okay.
Just a little context, it's kind of a dynamic programming principle, which historically was first used by one of our countrymen, Schauder, along with Michael Price, and sort of understood the zeros at the point at the regenerate critical point. I think we have to solve that particular algebraic variety of it. We sort of understood it. It was later on used by Savin and Silva in context. The answer is connected to that. But we don't do that.
I hope he doesn't get angry. And also, well, we can solve this, and the thing is that we can get this estimate. So, so this perturbation is really not that bad, no? So Q tilde is really close to Q, no? Okay, so there are two things. We have to find the coefficients, and we have to really not making don't go that far from Q, no? Okay.
Yeah, the exact stratification of the group algebra is important, where the next layer is only generated by polynomial. If something goes wrong over there, then what is going to be good? So besides the fact that we don't we need the homogeneous structure, besides stratification of the group algebra, the variables are important for the dynamic programming principle.
To work, yeah, exactly. So that's why, well, in Hormander vector fields we cannot do this because we don't have stratificate the Taylor formula and this thing. No, I don't know if we can.
Even if you use the Stein thing, you may have stratified structure, but you may not have the stratified structure. You may have the nilpotent structure, but not the stratified structure.
The stratified, okay, yeah. So this is an open problem, not to see if one can actually try to do these methods in the more general setting, like the one considered by Schauder. Okay. So with that, since Q tilde is not that far from Q, we have this estimate, and we are done with the proof, no? So we cook another approximating polynomial with this decay, no? And so the rest of the proof follows like this. So with this compactness lemma, we can prove that there is this polynomial, no? That has this, so this homogeneous polynomial degree less than k that satisfies this estimate, no? Okay. So, well, so this was in the identity because we translate. So we can do this for every point in this set. So we have this corresponding Taylor polynomial. And so the next step will be to prove this estimate, no? So I don't want to go into the details, but we really need for that this decay of the. So we really use that these are approximating polynomials, not in order to match, no, the boundary estimates with the interior ones. We really need this estimate for it too. If you go through the computations, you will see, oh, I really need this to really match, no? In the NORC1 alpha paper was kind of easy to get it, no? But this one is a little bit more complicated, no? And so, well, so hopefully the paper will come out soon, and so there are not only cosmetic changes to be done, and we didn't miss any part. But so these are some references if you are interested. This is the paper of Banerjee and Caffarelliin. So they prove it in smooth domains. This is the paper. just start gamma 1 alpha. Okay. And so these are some very inspirational papers. That this paper by Caffarelliin, and then these two by Savin, the Silva Savin, this other two. Okay. So, well, this one is more the one that we actually use, no? So I don't know if you have some question.
I would also like to invite the audience also to unmute themselves if they have any questions. If there are no questions, let us thank the speaker.
It seems like there is a question.
I was still thinking whether to ask this sort of thing, but can you consider negative values of
Negative?
values of alpha? Negative Holder cases. In the standard setting,
You mean this alpha?
yes. So
I don't know what the name is. Like some kind of formal tool.
yes, kind of.
So it's significantly rougher and so on.
Yes, it's a distribution. It's not a
Fair.
but you test it against it has some kind of decay.
Nice.
So there are some sort of systematic that you get even if you have at the distribution certain decay, and if you apply Laplacian inverse, then you get a function of the bit which has
Right.
certain determinant.
But I think this is kind of equivalent to it.
Yes, so here you have assuming alpha.
No, but what you are saying is that minus alpha is more like the dual of here. Really not minus alpha inverse.
It is a distribution.
I think this really works.
No, so that's why I was confused whether it was. So no,
But in the sense that, so Augmented cycle
yes.
or if that it is also
I did not get that.
even if you start with a distributional solution, it only makes for sub-Laplacian, because for our structure, distributional structure makes no sense. That's the way I did. But you can't do the possibility.
It is a classification. Yes. But how will this
Okay. I have no idea.
it's unprecise.
Yeah, we'll have to look at it now. You can show some papers.
Yeah, I also don't know what